Let's now work through a relatively basic Thevenin equivalent example. So this problem is exercise 2.28 from page 95 in the textbook. And what we want to do is find the Thevenin equivalent for the circuit shown on the slide here. And so of course we need two pieces of information. We need our Thevenin voltage and our Thevenin resistance. And if we have both of those, we then know our Thevenin equivalent. So recall from the previous video that if we find our open circuit voltage, we know that that voltage is simply equal to our Thevenin voltage. So that is our first step, is we'll just use our circuit analysis techniques to find this VOC, and that is then equal to our Thevenin voltage, and we're halfway there. So of all of the techniques that we've looked at so far, the most powerful is our node voltage, and we of course have that algorithmic approach, so hopefully that makes it a little easier to apply. So let's use our node voltage method to analyze this circuit. So we start by identifying our essential nodes. So again, anywhere that we have three or more elements connected. So we have one essential node up here at the top. This over here in the top left corner is just two elements, so that's not an essential node. Similarly over here, in this case, we don't include this output terminal because nothing is connected right now, but we have the 6 and the 10, so that's just a normal node. And then down at the bottom, we have, of course, 1, 2, 3, 4 elements connected, so that's another essential node. So we have two essential nodes in this case, so we know we can expect then that our N sub E minus 1 is going to be equal to our two essential nodes minus 1. So we're just going to have one equation to solve for. So this should be relatively straightforward. And once we have identified those essential nodes, we of course pick a reference node, as I've indicated with this blue arrow. We then define our node voltages, with the negative sign being at the reference node. So again, because we only had two essential nodes, I only have one node voltage, which I've labeled V1. So now we are going to apply KCL at each of our non-reference essential nodes. Again, in this case, we only have one essential non-reference node. So I've drawn my four currents leaving with the purple arrows indicated on the slide there. So I've kept that image of our circuit a little bit smaller here in the bottom right, and now we're going to write our KCL equation. And again, recall we're going to use Ohm's law and KVL to help get these currents represented by the purple arrows in terms of our node voltage, in this case V1. So if I'm looking at the current going out the left here, what I'm going to do is I'm going to define the voltage drop, voltage polarity such that the current's going through a voltage drop. I then apply my KVL, so I can say this voltage is equal to V1 minus 10 volts. So that's the voltage across my 20 ohm resistor, V1 minus 10. So then of course I use Ohm's law. That voltage divided by 20 gives me the current through that resistor. The current through the bottom, let me erase that line so we can more clearly see that 5 ohm resistor. So we've just got V1 over 5. So there's our second current. For the third current, it's just a current source, but it's going in the opposite direction of the purple arrow, so we have -1. And for the last current, this is going out the right, we have the 6 and the 10 ohm in series, so I just add those two and the voltage across them is V1. So again, we've ignored these sort of output terminals because nothing is connected there. So essentially, we could just say that this VOC is really just the voltage across this 10 ohm resistor. So that's what we're interested in. So what I'm going to do now is what I had mentioned in some of the previous videos where we were doing node voltage analysis. In the previous videos, what I did was multiply by a common, least common multiple of the denominators here. So in this case, I've got 25 and 16, so that gets a little bit messier. And oftentimes to avoid making a simple math mistake, what I'll do is I'll just keep those fractions. So I've just factored out here, we've got V1 is multiplied by 1/20th in this first term, V1 is multiplied by 1/5 in the second term, and V1 is multiplied by 1/6 in the fourth term, or sorry, rather 1/16th. So I just keep all of these factors that are multiplying by V1. I move my constant terms to the other side, so I've got -10 over 20 becomes +10 over 20, and my -1 becomes +1. So I'm just keeping all the fractions, again, to avoid making a simple math mistake when sort of simplifying that. So then I can plug that into the calculator and I see that my V1 is 4.8 volts. So now we know our node voltage, so now we're on to step 6 of our node voltage analysis method, and that is to use our node voltage to find other voltages of interest. So as we had said earlier, let me change my pen to a different color here. Let's do green. So we'd said V1 is the voltage across both of these resistors, 6 ohm and 10 ohm in series, but really we're just interested in the voltage across the 10 ohm resistor. So if we have voltages in series and we want voltage across one of them, that sounds a lot like what we've done before with our voltage division. So now we're going to use voltage division, and we can say that our Thevenin voltage equals our open circuit voltage, which is our V1 times the resistor ratio. And so we're interested in the voltage across the 10 ohms, so we put the 10 in the numerator. And then in the denominator, we put the sum of all of the resistances in series. In this case, it's just the 6 and the 10 ohm. And we get that our Thevenin voltage is 3 volts. So there's half of the problem solved. We have our V Thevenin. Now we just need to figure out what our Thevenin resistance is. So we're going to look at one method in the remainder of this video, and we'll come back in the next video and look at an alternate method. But let's say we stick with our sort of more straightforward algorithmic approach of we now have our VOC, and we know that from a previous video we had our R Thevenin is equal to that VOC divided by our short circuit current, ISC. And so, of course, again, we already know the value of the VOC. We just saw on the previous slide that that was 3 volts. So if we find I short circuit, we can then calculate our Thevenin resistance. So I've modified our original circuit here, and we've taken those output terminals and we have shorted them together. So I've just drawn a conductor between those two, and I've labeled the current through that as I short circuit. So notice now we have a short circuit in parallel with the 10 ohm resistor. So we say that our 10 ohm resistor is shorted out. So we basically ignore that in our analysis. So we could redraw the circuit and just not include that 10 ohm resistor, and we're trying to find then just this short circuit current. So we can again use our node voltage analysis. So the steps are pretty much identical. So we identify our essential nodes, we choose one to be the reference node, we label our node voltage, we label our currents leaving that non-reference node, and the equation is actually going to be very similar as well. So the current going out the left is unchanged, so we still have V1 minus 10 over 20, which makes sense because nothing has changed in this left loop. Same thing for the two currents going out the bottom, so no change for these two components here, which are represented in these two terms in the equation. We do, however, have a slight change in this last equation because notice now we no longer have that 10 ohm resistor, so this fourth term is just V1 over 6. So whereas before we had 6 plus 10 in the denominator, now we just have 6. So again, I'm going to use the same technique of just factoring out these fractions, not trying to worry about simplifying it to whole numbers. So we have V1 times this collection of fractions. I've moved my constants over to the other side. I solve and I get that my V1 is 3.6 volts. But I'm interested in my short circuit current. So now I can say my short circuit current is actually just that current that was going out the right of that node, V1 over 6. So plugging that in, I get that my I short circuit is 0.6 amps. Now we know VOC, we know ISC, so we can go back and say that our Thevenin resistance is 5 ohms. We put that together with our Thevenin voltage, which we found earlier to be 3 volts, and here is our Thevenin equivalent circuit.